The transformer architecture is the engine running almost every major AI model in existence. ChatGPT, Claude, Gemini, Llama, Grok. All of them built on transformers. All of them subject to the same fundamental bottleneck. A paper from researchers at Nvidia, MIT, and ByteDance is getting fresh attention in AI research circles this week, for a result that speeds up transformer decoding by 1.7 times. Without any new hardware. One architectural change. That is all. The research is called SparDA, sparse decoupled attention. And understanding what it does requires understanding the problem it solves. Let me explain how transformers currently work during inference, when you are generating a response. Every time a language model generates the next token, the next word or word fragment, it needs to look back at everything that came before. This is called attention. The model attends to every previous token in the context to decide what comes next. To do this efficiently, modern transformers use what is called a KV cache. As each token is generated, its key and value representations are stored in a cache. The next token looks up all previous tokens in that cache. The problem: the KV cache grows with every generated token. As responses get longer, as context windows get larger, the cache grows. Accessing a large cache takes time and memory bandwidth. This is the speed limit on inference. An earlier approach called sparse attention tried to address this. Instead of attending to every cached token, the model scores the cache in blocks and only attends to the top k most relevant ones. This cuts attention computation and bandwidth. But sparse attention left a problem unsolved. Selecting which blocks to attend to still has to happen before the layer can run, and fetching those blocks from memory takes time the model spends waiting. SparDA takes a different approach. It adds a fourth projection to each attention layer, alongside the usual query, key and value, called a forecast projection. Here is the key insight: the forecast projection predicts which blocks of the cache the next layer is going to need, before that layer even starts computing. That means the system can start moving those blocks from CPU memory to the GPU in advance, while the current layer is still working. The slow part, moving data, happens in parallel with computing, instead of the model waiting for one before starting the other. The practical result: decoding speed increases by 1.7 times over the existing sparse attention baseline it improves on. On reasoning benchmarks, on one of the two models researchers tested, accuracy improved by 6.5 points. Both numbers matter. But the accuracy improvement on long reasoning is arguably the more interesting finding. Here is why. The models that have been making the biggest headlines recently, Anthropic's result improving a long-standing bound tied to the Riemann hypothesis, the complex agentic tasks, these are long reasoning tasks. They involve the model working through many steps of logic over long contexts. The bottleneck in long reasoning is not just speed. It is also accuracy degradation over length. As the context gets longer, as the reasoning chain gets more steps, small errors compound. Models sometimes lose track of where they are in a reasoning chain over very long outputs. A 6.5-point accuracy improvement on reasoning tasks alongside a 1.7 times speed increase is a meaningful double improvement. Not a trade-off. Both directions improved on this benchmark. Now the hardware question. SparDA is an architectural change. It runs on existing transformer hardware. No new chips required. No new accelerators. No new data center build-out. This means any deployment running transformer models on existing Nvidia GPUs could in principle benefit from this improvement through a software update. The improvement does not require buying new hardware, it requires updating the model architecture and inference stack. For companies running large inference workloads, where compute cost is measured in hundreds of millions of dollars annually, a 1.7 times speed improvement on the decoding step translates directly into a meaningful reduction in the compute required to serve the same number of requests. That is a real cost reduction from an architectural paper. Nvidia publishes research like this and sometimes incorporates it into its inference software stack, TensorRT-LLM, which is what many enterprise deployments use. If SparDA is incorporated into that stack, the improvement could reach production deployments without requiring any changes at the application level. Here is what I find genuinely interesting about this result. Most AI news is about new models. Bigger models. More parameters. Higher benchmark scores. This is not that. This is a result about making the models we already have run faster and more accurately, with the hardware we already have. In a field defined by the race to build the next thing, a result that improves the current thing without new resources is a different kind of progress. Subscribe for daily AI coverage. Comment below. Developer question: if you run inference workloads in production, what is your current biggest bottleneck? Speed, cost, accuracy, or context length? Tell me. I read every comment.